Hi, this is Kate, and we're learning about exponential decay. Before learning about exponential decay, you should already have an understanding of exponential growth. This equation, y equals 5 times 3 to the x power, is an exponential growth equation and corresponds with one of these tables. Can you choose the table that corresponds with the equation? That's the table in choice C. In this equation, the 5 represents the starting value. It's the value of y when x is 0. It's also the y-intercept on the graph of this equation. The 3 represents the growth factor of the relationship. Whenever the input x is increased by 1, the output y is multiplied by 3. 5 times 3 is 15, 15 times 3 is 45, and so on. A decay equation is similar to a growth equation, except the quantities will decrease by the same factor instead of increase. This first quantity still represents the starting value. Since we're going to start with something, get smaller and smaller, we'll start with kind of a large number. I'm going to choose 81. In this table, the y values decrease by the same factor every time, and the base of this exponent will be called the decay factor. 81 times something is 27. 27 times something is 9. 9 times something is 3. What would we have to multiply by every time to get the next value? What is the decay factor in the table? The decay factor is 1/3. You may have noticed that 81 divided by 3 is 27. 27 divided by 3 is 9. Well, dividing by 3 is the same as multiplying by 1/3. So the base of the exponent in our equation will be 1/3. The graph of an exponential growth equation looks something like this. When x is 0, y is 5. Every time x increases by 1, y is multiplied by 3. So we go up to 15, and then when x is 2, we'll multiply by another 3, go up to 45. So this was our decay equation, 81 times 1/3 to the x. Every time x increases by 1, y decreases by a factor of 1/3. Which graph do you think corresponds with this equation? Graph A corresponds with the equation. The starting value is 81. Every time x goes up by 1, we get 1/3 of the previous y value. So 81 goes to 27, times 1/3 is 9, times 1/3 is 3, and so on. Now you may be thinking, if I keep taking the y value and multiplying by 1/3, I'm never going to get to 0. I take 1/3 of something, then 1/3 of it, then 1/3 of it, then 1/3 of it. It gets smaller and smaller and smaller, but it never actually goes away. So this is a feature of exponential functions. They get closer and closer to a line that they never actually touch. The y-coordinate of this graph never gets to 0. This horizontal line that the graph gets closer and closer into, but never actually touches, is called an asymptote. So to summarize, this is sort of the generic form of an exponential function. The x and the y represent the input and the output of the function like normal. This number here we often called a. We can say it's the initial value of the function. It's the value of y when x equals 0, and if we graph it, it's the y-intercept of the graph. The number we use for the base of the exponent determines how the function changes as x changes. If b is a number that's greater than 1, it's an exponential growth equation, and this is called the growth factor. As x gets bigger, y gets bigger. If the base of the exponent is in between 0 and 1, so it's maybe a fraction like 1/2 or 1/3, but really any value between 0 and 1, it's called a decay factor. As x gets bigger and bigger, y gets smaller and smaller. The graph of a growth function has this shape anytime b is greater than 1. A is right here, it's the y-intercept. The graph of a decay function will look like this. As x gets bigger, y gets smaller. This happens anytime b is in between 0 and 1, and a is still right here. It's the y-intercept. The half-life of a radioactive isotope tells you how much time passes before half of it degrades into a neutral, non-radioactive substance. So for example, if we look at this particular atom, polonium-218, its half-life is 3 minutes. If we start out with 256 grams, then after one half-life, there will only be 128 grams of radioactive substance. After 2 half-lives, which is 6 minutes, there will be 64 grams remaining. How much radioactive polonium-218 is remaining after 4 half-lives? After 4 half-lives, there will be 16 grams remaining. After 3 half-lives, it gets cut in half again, 32. So after 4 half-lives, cut in half again, 16 grams. Look at the equation carefully and think about your understanding of exponential functions. Which equation relates x, how many half-lives have passed, to y, the amount of radioactive polonium-218 remaining? Choice A is correct because 256 was the starting value, and the decay factor is 1/2. So think about this. If we want to know how much is remaining after 15 minutes, well, 15 minutes is 5 half-lives because a half-life is 3 minutes. We need to take the 15 and divide it by 3. If we want to know how much remains after t minutes, we'll have to take whatever t is and divide it by 3 to get the number of half-lives. So in general, our half-life equation looks like this. We want our exponent to be the number of half-lives, so we need to take the amount of time and divide it by the half-life of the isotope. This is Kate, and we've been learning about exponential decay.